All right, everybody. The clock just turned to 10:30, so I'm going to jump in and get started. First off, good morning, everybody. Hi. Happy Thursday. Can you believe it? Another week is almost over. Yeah, this is going by fast. So that being said, let's jump into today's warm-up question. So today we begin to learn about what I consider to be some pretty cool stuff, but it's also very theoretical. And so I think it's important to really start with the practical application of it. And here's what that practical application is. I don't know how many of you have lived in the Bay Area for much of your life or have lived here in Silicon Valley for much of your life, but believe it or not, San Jose is actually one of the driest places in the entire Bay Area. And just for reference, if you go onto Highway 17, go across the hill and go to Santa Cruz, they receive about twice as much rainfall as San Jose does. On average, they receive about 31 inches a year. We here in San Jose only receive on average about 15 inches a year. Make a guess as to why. And to respond to that, I have opened up the Google form and it's linked right there. So take a moment, and as always, no penalty for a bad guess. Well, there is no bad guess, like any guess is good here. But take a guess and then we'll actually get into today's topic and talk about how it applies to this situation. All right, a few more people have trickled in. I will paste this link a few more times as people trickle in. Take about 3 or 4 more minutes. More people have trickled in now. And more people. As I see people coming in, I'm just repasting the link. Let's see what people have to say. Okay, let's stretch that. Minimize that. There we go. Here we go. I will paste it again. Let's take about another 2 minutes. right, it looks like I've gotten almost everybody's responses. I know a few people still need to finish writing up, and that is totally fine as always. But let's see what people have to say. Okay, so maybe because Santa Cruz is located along the Pacific Ocean, so maybe it's because it's right next to the ocean. We're a little bit inland. And then the mountains located between both of the cities. Not many of these rain clouds make it to San Jose. So maybe something to do with the mountains. I'm guessing it is because of the surrounding terrain. So it's again something to do with the mountain. I think Santa Cruz gets more rain than San Jose because of the water cycle and the fact that it's surrounded by ocean and beaches. All right. More mountains and air collides with obstacles in the landscape have to rise. Santa Cruz gets twice as much as San Jose does because it's located near the coast. Near the coast, on the beach, next to a large body of water, directly on the coast, while San Jose is fairly landlocked. Let's see here. It could be slightly different climate. Santa Cruz is closer to the beach, close to the water. The Santa Cruz Mountains moist air cools and condenses into fog, which makes it receive more precipitation. Ooh, somebody was accessing something from last time. So yeah, on the Santa Cruz side of things, they get a lot of upslope fog, and so that can influence things. The amount of hills and mountains that cause rainfall in Santa Cruz, so that might be a factor. Close to the ocean and mountains, elevation increase, more moisture in the air because it's closer to the ocean. Santa Cruz is more humid. So it seems like the two prevailing themes I'm getting here. I'll just skim the rest of these real quick just to make sure. But it seems like, yeah, I mean, just looking from these, it really seems like the two prevailing themes that I'm getting here are that San Jose is inland, whereas Santa Cruz is located near the coast, and that greatly influences how much rain we get. And then a lot of people mentioned something about the mountains, that there are mountains between here and Santa Cruz, and so those mountains play a huge role in this as well. Well, actually, both of those are correct answers, and both of those actually do play a role in our precipitation pattern here in San Jose and why we get so much less rainfall than our friends over in Santa Cruz. So let's dig into that. Let's actually talk about that a little bit today. I do want to give one disclaimer about today. Well, today and next time, this is probably the most theoretical and mathematical stuff we do in the class. Don't worry, it's still not super crazy, but it is very easy to feel stuck, to feel like you're struggling. Please, please, please take advantage of the chat. If you are stuck, send me a message. I'm stuck. And I will stop and we will go back over something. If you have questions, please don't hesitate to ask them. And also, it really does go downhill from here. Like this and next class are probably the toughest topic in the entire course, though it's still really cool stuff. So let's jump in and talk about it. Sorry, I've been having this frog in my throat for a while. So today and next time, we're going to be talking about the concept of stability. And stability greatly governs air's ability to rise or not. In an unstable atmosphere, you get a lot of rising air, and that rising air then creates lots of storm systems. Whereas on the other hand, in very stable air, which is what we get whenever we have bad air quality, a lot of the air near the ground can't rise. Instead, it's just compressed near the ground. And so anything that's in that air, pollution, smoke, anything that's in that air is stuck near the ground. But before we can really talk about stability, we need to talk about this concept called adiabatic cooling. And so that's what we're going to talk about today. Adiabatic cooling. So let's do it. So our goals for today are first to understand how air cools as it rises and how moisture in that air affects how it cools. And then we're going to apply this to those precipitation differences I mentioned between San Jose and Santa Cruz. So let's do it. Let us jump in. So for today's topic, there are really three main concepts that are necessary for understanding it. The first concept is this concept called an air parcel. The second concept is called adiabatic. And then the third concept is actually a few things, what are called adiabatic lapse rates. These are rates of cooling. So air parcel, adiabatic, and adiabatic lapse rates. And don't worry, I'm going to go through each one of these in a little bit of detail. So without further ado, let's talk about them. So an air parcel is a theoretical bubble of air. Rather than treating the atmosphere as one big blob of air, meteorologists actually treat the atmosphere as trillions and trillions and trillions of tiny little bubbles of air that are completely independent of one another. What that means is that they don't affect one another. And we call these little bubbles of air parcels. Think about like a bubble or a balloon. One of the important things to know about this bubble is that with one exception, and I'll tell you what the exception is in a little bit, with one exception, what happens in the parcel stays in the parcel. I like to call that the Las Vegas rule. Just like the slogan for Las Vegas, what happens in Vegas stays in Vegas. Well, what happens in these air parcels stays in these air parcels. The only exception to that is if something in the parcel changes phases. What that means is that it goes from gas to liquid or gas to solid. That's the only exception. Other than that, what is in the parcel stays in the parcel. Now, one of the things I will stress really quickly in case anybody asks why, this concept isn't 100% true. But exchanges between one air parcel and another can oftentimes be very complex, and they're very, 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 very small. So in order to simplify this concept, we just say they're really, really small and it's not worth all the trouble modeling them. So as a result, we are just going to say that the parcel is completely isolated from its surroundings. And like I said, that's not 100% true, but that's like 99.999% true. Good enough for this class, good enough for meteorology, I promise you. But then again, little things like that are why weather forecasts will never be 100% perfect. And there's a lot that goes into that. I'm not going to talk about that right now. That goes off into a tangent and no time for that. So it's important to note that these air parcels are, as I just mentioned, they're essentially isolated from their surroundings. What that means, the importance of that, is that they don't rub up against each other. They don't exchange things with one another. They don't share things. They don't split things. They don't bump together and collide. They don't pull apart. They don't do any of that. Instead, what is happening inside that parcel is completely independent of what is happening in the outside atmosphere. That is incredibly important to know. Because if that wasn't the case, then these parcels would be way, way, way more complex and way, way harder to deal with. So what is happening inside that parcel of air is independent of what is happening outside. Now, there are a few examples of air parcels that even you can see. If you've ever driven by a factory and you see a bunch of smoke coming out of that factory, you can treat that smoke as a bunch of individual air parcels. Or if you're a hang glider and you're looking for thermals, if you remember, a thermal is a big bubble of warm rising air. That is an air parcel. If you've ever seen smoke coming off of a fire or pollution near the ground, that pollution is made up of all kinds of little air parcels. There are some times where I've seen smoke come out of a factory chimney and then suddenly it just fans out. It's not able to keep rising. It just fans out. Well, the reason why that happened is that all of those air parcels that were trying to rise, something kept them from rising. And we'll talk about that something next time. But let's actually dig into how these parcels behave. So, quick review. If I have a parcel of air and I release it to rise in the atmosphere, what will the parcel do as it rises? Give you a hint, corny dance. What will it do? It expands and it cools. Bingo. If you remember my corny dance, air expands, it cools. Something else happens too. We'll talk about that later. For right now, it expands and cools. Now, what happens if the parcel sinks? What will it do? If the parcel sinks, what will it do? Opposite. It compresses and it warms. Bingo. The parcel contracts and it warms. Now, up to this point, I've pretty much said this. I've said, as a parcel rises, it expands, it cools. But the thing I haven't actually mentioned yet is, how much does it cool? Well, believe it or not, there's actually a set rate that the parcel cools at. And this is why simplifying this really helps make this a lot easier to work with. Let me tell you what I mean by this. So this parcel exchanges nothing with its surroundings. As I mentioned, the only example or the only exception to that is when air undergoes a phase change. Then if water condenses, that water falls out. That's really the only exception. Otherwise, what's in the parcel stays in the parcel. That includes matter, that includes all the gases, that includes the energy, the heat that's in the parcel, that all stays the same. But we actually have a fancy name for that process. So just to review, as air rises, it expands and cools. As it sinks, it compresses and warms. It contracts and warms. Well, the name of this fancy process that air undergoes as it rises is what is called an adiabatic process. So a diabatic process is a process where two things are exchanging heat with one another. So a diabatic process is a process where two things are exchanging heat with each other. Usually when you stick an A in front of that, kind of like atheist, or trying to think here of some other terms, but like atheist is oftentimes the common one. A usually means without. So an adiabatic process is a process without heat exchanges happening. So an adiabatic process occurs when a parcel of air does not exchange heat with its outside environment. As a result, as our parcel of air rises, it's cooling adiabatically. It's cooling adiabatically. Now here's the good news with this. The good news is that if we assume an adiabatic process, that gets rid of a lot of crap. Let me give you some examples. That gets rid of radiation. Don't have to worry about radiation affecting our parcel. That gets rid of conduction. One parcel rubbing up against another one, we don't have to worry about that. That gets rid of advection. So cooler air moving in and cooling the parcel down, we don't have to worry about that. So all of these other complex things that are very hard to model and would make this way more difficult than it's worth are taken out of the picture. And instead, we assume that there is a set amount of heat, a set amount of energy inside that parcel. And so as it rises, it actually undergoes cooling at a set rate. And that set rate is caused by two things. The first one we've already talked about, which is expansion or contraction of the parcel. If the parcel expands, it cools. If it contracts, it warms. The other concept, I remember last week warning you when I introduced the concept of latent heat, I said, this will be very important next week. This will be very important as we get into chapter 5. Well, we are now here. Because embedded in that parcel is atmospheric air. And atmospheric air is made up of nitrogen, oxygen, argon, neon, carbon dioxide, and some water vapor. Well, remember, as something cools, its temperature gets closer and closer and closer to the dew point temperature. And if you remember from last time, the dew point temperature is the temperature that air is cooled to in order to become saturated. So as this parcel is rising and expanding and cooling, it's getting closer and closer and closer to saturation. Well, once it becomes saturated, water begins to condense. Who can remind me, as water condenses, what does it do with latent heat? Does it take in latent heat? Does it absorb heat from its surroundings? Or does it release heat to its surroundings? So when moisture condenses, I've got one vote in chat. Jerome says it releases. Anybody want to argue against that? Jerome is correct. Yeah, as the moisture in that parcel takes that step down, as it goes from a gas to a liquid, it releases heat into our parcel. So it's just these two things that affect the temperature of our parcel. And because these are the two things that affect the temperature of our parcel, we can actually model pretty easily what a parcel does as it rises in the atmosphere. And we have tons and tons and tons of observation to back these approximations up. So let's talk about them now. So there are two adiabatic processes that I need to talk about. The two adiabatic processes are called dry adiabatic and moist adiabatic. Sorry about that. Dry adiabatic and moist adiabatic. A parcel cools dry adiabatically when its temperature is greater than the dew point. At that point, the air is unsaturated. And so as the parcel is rising, expanding, and cooling, there is no net condensation happening inside the parcel. Since there's no net condensation, there's no latent heat release. So that is a dry adiabatic process. On the other hand, as the air is rising, it's expanding, it's cooling, it's getting closer and closer and closer to the dew point. Eventually, it will reach the dew point. At that point, the air becomes saturated, moisture begins to condense, and latent heat is released. In that case, the parcel will cool moist adiabatically. In that case, the parcel will cool moist adiabatically. So let's actually do something with this. Here's the good news with these two processes. Because we have simplified it down to just two things, we can actually give or use a set rate of cooling. Rather than using a weird complex model, I can just give you a set rate of cooling. And here we go. For a dry parcel, for a parcel that is not saturated, for a parcel where the temperature is above the dew point, as the parcel of air rises in the atmosphere, it cools at a rate of 10 degrees Celsius per every 1,000 meters. So 10 degrees Celsius per every 1,000 meters. What this means is if I have a parcel of air at the ground and I release it and it floats up 1,000 meters, it cools by 10 degrees. We're actually going to stick with metric here. And the reason why is because the numbers are just prettier. They're easier to work with. They're easier to count. They're not tricky. So we're going to stick with metric here because all we're doing in this case is we're just subtracting 10, subtracting 10, subtracting 10. For every 1,000 meters we go up, we subtract another 10. Let me show you what this actually looks like or what this means. So, if you have a parcel of air at the surface and it has a temperature of 30 degrees Celsius and you let it rise, as it rises to 1,000 meters, it cools by 10 degrees. As it rises to 2,000 meters, it cools by another 10 degrees. Would anybody like to take a shot at what the temperature of this parcel right here on the picture, what it would be at 3,000 meters? So if I were to draw 3,000 meters up here, what would the temperature of my parcel be? Getting lots of votes for 0. Yes, yes, yes. So yeah, if we shot up another 1,000 meters, assuming that the parcel is still dry, which in this case, that's fine, it would be 0 degrees Celsius. And simply put, for every 1,000 meters you go up, you just keep subtracting 10, subtracting 10, subtracting 10. For those of you who are comfortable with math and comfortable with working with equations, you could put together a really simple equation. For those of you who aren't, I recommend drawing a picture like this and just at the surface start with 30. Then for 1,000, you just subtract 10. 2,000, you subtract another 10. 3,000, you subtract another 10. And you just keep going like that. That process just keeps going and going and going like that. So that is a dry, unsaturated parcel. So that is for a dry, unsaturated parcel. However, actually, before we do that, let's do an example. So, and what I will do is I will do this the picture way. So a parcel of air with a temperature of 40 degrees Celsius is released into the atmosphere and cools dry adiabatically. What is its temperature at 4,000 meters? So what I like to do is draw a picture. So here's 0. Here's my parcel of air. It has a temperature of 40 degrees Celsius. And then I'll draw 1,000 meters, 2,000 meters, 3,000 meters, and 4,000 meters. Sorry for my terrible handwriting using this drawing pad. So if I let it go up 1,000 meters, I'm subtracting 10 from it. So now my bubble's a little bit bigger because the parcel expanded. And the temperature is now 30 degrees Celsius. Go up again to 2,000 meters. Parcel's a little bit bigger now. And my temperature is 20 degrees Celsius. What about 3,000 meters? What would my parcel be at 3,000 meters? It'd be 10. Bingo. It would be 10. And then finally, at 4,000 meters, it would be 0. So that's the way to do it, really. Now, if you're comfortable with the math, the way that you can do it is the temperature at 4,000 meters is equal to the temperature on the ground minus rate times height. So our temperature on the ground was 40. Our rate is 10 degrees Celsius per every 1,000 meters. And our height is 4,000 meters. Meters go away. Those 3 zeros go away. So you ultimately get 40 degrees Celsius minus 10 times 4, which is 40 degrees Celsius, which equals 0 degrees Celsius. So for those of you who are comfortable using that equation, by all means, use it. For those of you who aren't, drawing a picture is just perfectly fine with me as well. So before I continue on, questions, comments, concerns, things to throw at me? Damn it, Terrence, you're making me do math. It really doesn't get much worse than this. It really doesn't. Okay. When does it normally stop rising? We will actually talk about that next time. So there are different factors that affect its ability to rise. So today, for the purpose of today, I'm just going to say, let it rise. Just assume it's going to keep rising. But next time, we'll actually talk about what actually factors into its ability to rise. Great question. Now I can give you a super short answer once it hits the tropopause. After that, it's hard for things to rise. But we'll talk about why next time. Great question, Jerome. Okay. So here are the answers. So at 1,000 meters, it was 30. 2,000 meters, it was 20. 3,000 meters, it was 10. 4,000 meters, it was 0. All right. Now let's actually suppose that the parcel is saturated. So instead of looking at a dry parcel, we are now looking at a saturated parcel. No, it will not always stop at 0. If I went up to 5,000, it would be -10. 6,000, it would be -20. 7,000 would be -30. So it will continue. And that's actually a really good piece of feedback for me. I should probably include an example that shows that it does continue beyond that. In fact, just to do that justice, at 5,000, it'd be -10. And so on and so forth. So it would just keep going. The temperature would just keep going down, 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 down. Theoretically speaking, it could reach absolute 0, but it would have to rise really, 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 really high. And yeah, don't worry about that. And there are other processes that would actually stop that from happening. Okay, oops. All right, so now let's assume our parcel is saturated. In a saturated parcel, moisture is condensing. That moisture actually leaves the parcel and becomes clouds. But before it leaves, it gives a little parting gift, and that is latent heat release. So as the moisture is condensing, it releases latent heat. Now, this little release of latent heat doesn't actually stop the process, doesn't stop the parcel from cooling, but it does slow it down. So instead of cooling at a rate of 10 degrees per every 1,000 meters, the parcel now cools at a rate of 6 degrees per every 1,000 meters. So again, instead of cooling at a rate of 10, it now cools at a rate of 6. And the reason why this is because as the parcel is cooling and condensing, latent heat is being released. So that's why this happens. Latent heat is being released. Well, let's do an example of that. I'll actually do an example of this one really quickly. Let's say we have our same parcel from the last example. A parcel with a surface temperature of 40. And we allow it to rise. What would its temperature be at 1,000 meters in this case? It would be 34 in this case. Why? Because instead of subtracting 10 like we were for a dry parcel, we're subtracting 6 for a moist parcel. And then 2,000 meters. What would its temperature be at 2,000 meters? How about other than Jerome and Dow? Want to make sure other people are getting this. Not quite. 28. Yes, yes, yes. 28. And so on and so forth. As it keeps going up, in this case, you would subtract 6, you would subtract 6, you would subtract 6, you would subtract 6. And the process would just keep going. So let's actually do a few more examples of this. Rather than doing this as an assignment, let's actually do this together as a class. So let's suppose that the air is really dry, and therefore the parcels are unsaturated, and smoke from a fire rises. At the surface, the temperature of that smoke was 60 degrees Celsius. So the surface temperature, our parcel had a temperature of 60 degrees Celsius. What would the parcel temperature be at 1,000 meters? In this case, it's a dry parcel. 50. Yep. It's a dry parcel, so we are using the dry rate. Okay. What about 2,000 meters? $40. 3,000 meters. 30. 4,000 meters. 5,000 meters. You see where I'm going with this? 6,000 meters. 7,000 meters. 8,000 meters. Typed it in before I even finished saying it. 9,000 meters. Damn, you all are quick. And at last, 10,000 meters. Negative 40 degrees Celsius. So just to help people keep track, 2,000 meters, it was 40. 3,000 meters, it was 30. 4,000 meters, it was 20. 5,000 meters, it was 10. 6,000 meters, it was 0. 7,000, it was negative 10. 8,000, negative 20. And 9,000, negative 30. And then 10,000, negative 40. All right. Now let's suppose that there's steam in the smoke, and therefore all the parcels are saturated. They are moist, they're wet, they are ready to go. I just thought of a really, really bad joke with a recently related song with 3 letters to it. I'll just say wet A parcels. So let's assume that these parcels are moist. Okay. That has WAP. Wet ass parcels. Okay. That's okay. So let's assume that we now have saturated parcels. Yikes. And everything else is the same. So we start once again with a temperature of 60 degrees Celsius at the surface. But now our parcel is moist. So instead of cooling at a rate of 10, it now cools at a rate of 6. So its temperature at 1,000 meters would be, as people are typing in, 54. For 2,000 meters, what would it be? 48. I should keep drawing the bubble. That's not like sacred, I just do it because. Okay, what about 3,000? 42. 4,000. 36, 5,000, 30, 6,000, 24, 7,000, 18, 8,000, 12, 9,000, 6, 10,000, 0. Bingo. Now, one of the things you'll notice here is that a moist parcel can end up being much, much warmer than a dry parcel. That is one of the factors that really affects a parcel's ability to rise. If it is a moist parcel, it will rise. If it is a dry parcel, it might not be able to. That felt like torture where they force you to count backwards by 7 from 1,000. Somebody just private messaged me that. I won't ever make you go all the way up to 10,000 meters. But that's really what you're doing here. So for a moist parcel, for every 1,000 meters, you're subtracting 10. Oh yeah, sorry, for a dry parcel, you're subtracting 10. For a moist parcel, you're subtracting 6. Now that being said, I was going to do this as a think, pair, share, but I think I would rather just talk about it as a class. As air rises, it expands, it cools, and usually air on the ground starts out as dry. As it rises, it expands, it cools, and moisture in it condenses. So let's say we start with a parcel that's dry at the surface, then it rises. At some point, it becomes saturated. At some point, it becomes saturated. What will we do? Will we continue using our dry rate, or will we switch to our moist rate? Instead of writing this down, type your thoughts in chat. Will we continue using the dry rate, or will we switch to the moist rate? So if a parcel becomes saturated as it rises, will we stay at the dry rate, or will we switch to the moist rate? All right, I'm getting a large number of voices that are saying switch. One person messaged me dry. They said, how will we know when it's moist? We're about to get to that. So that's the second question. The correct answer is we would switch. Once a parcel becomes saturated, you switch from 10 to 6. So if the parcel starts on the ground dry, it's rising, it's cooling by 10, by 10, by 10, and then it becomes saturated, we switch to 6. Now, how do we know that that's happened? So how do we know that a parcel has cooled to saturation? What temperature could we use to tell us if it's cooled to saturation or not? Jace, great job. Alan, great job. Jerome, great job. Yes, yes, yes. We look at the dew point. I know this is basically a continuation of what we were talking about last time. The dew point is the temperature that air cools to in order to become saturated. So what we would want to do is, as our parcel is rising, we would want to compare it to the dew point. if the temperature of our parcel, using a very physicsy notation here, the temperature of the parcel, if the temperature of the parcel is greater than the dew point, then the air is unsaturated. On the other hand, if the temperature of the parcel is equal to the dew point, then the air is saturated. Now, I assume that this is begging a question that a few people probably want to ask right now, which is, what happens when the parcel temperature is colder than the dew point? For the purpose of this class, that won't happen. That's a condition called supersaturation. In that case, any excess moisture spontaneously spontaneously condenses. Spontaneously combusts. All of a sudden you look outside, there's like big explosions of clouds. No, that's not what happens. It spontaneously condenses. And then that causes the dew point to drop down to the temperature. So once the parcel becomes saturated, the temperature and the dew point will always stay the same. As long as the parcel continues cooling, the dew point will continue cooling as well. And that's because moisture is condensing. Let's actually talk about that for a few seconds. So, how do we know if a parcel is saturated or not? Well, we look at the dew point. So, for most cases, I will give you something like a parcel of air with a temperature of, I'll say 16 degrees Celsius and a dew point of, I'll say 8 degrees Celsius. In many cases, I will give you something like this, a parcel of air with a temperature of this and a dew point of this. The very first thing you want to do before you do anything else is check for saturation. How do you do that? Well, you compare the temperature of your parcel to the dew point temperature. You compare this to this. In this case, the parcel has a temperature of 16. The dew point is 8. In this case, is our parcel saturated or not? In this case, is our parcel saturated or not? We have a temperature of 16 and a dew point of 8. I've got 3 votes right now in chat, all saying that it's not saturated. And I would agree with Giovanna, Alvin, and Carlos, and somebody who private messaged me right now. This is not a saturated parcel. So right here, it is unsaturated. So for my parcel of air, what rate of cooling would I use if it wasn't saturated? Would I use 10 or 6? Carlos and Giovanna, I would use 10. So my parcel's temperature at 1,000 meters would be 6. Now here's the tricky thing about the dew point. In addition to the parcel having its own lapse rate, the dew point also has its own lapse rate. As air rises, it enters into a lower pressure environment. The lower the pressure, the cooler the dew point. For every 1,000 meters, the dew point cools by 2 degrees Celsius per every 1,000 meters. So what would my dew point be at 1,000 meters in that case? So I've got my temperature of 6 at the equator, or is that at the equator? Oh my gosh, at 1,000 meters. Yikes. What would my dew point be at 1,000 meters? If it cools by 2 degrees for every 1,000 meters. Got one person voting in chat. I'd like to hear from a few more people. Okay, now I've got the mark of the beast in chat. Okay, now I don't. 6, 6, 6, 6, 6, 6, 6. I would agree. So the dew point in an unsaturated environment cools by 2 degrees. So it too also equals 6 at 1,000 meters. Oh, let me put that 1,000 there just to clarify that it's at 1,000 meters. What do you notice in this case? What do you notice about our temperature and our dew point?
They're the same.
They are the same. Yes, yes, yes. At this point, is our air saturated or unsaturated? It is now saturated. So just for kicks and giggles, what would our temperature of our parcel be at 2,000 meters? Now, what would our parcel's temperature be at 2,000 meters now? So I've got 3 votes for 0 in chat right now, 4 votes for 0, 5, 6, 7. So here's what happens. Once the parcel becomes saturated, that lapse rate switches from 10 to 6. So instead of subtracting 10, for the remainder of the parcel's ascent, we're going to be subtracting 6. And the parcel is now 0 degrees Celsius. Now what happens is once a parcel becomes saturated, moisture is condensing, and that condensed moisture leaves the cloud. The end result of that is that our parcel cools at a rate of 6, but so does our dew point. If parcel is saturated. And the reason why is because any moisture that condenses gets kicked out of the parcel. That is the one exception to the Las Vegas rule. A parcel that condenses gets kicked out. So our moisture that condenses gets kicked out. That causes the dew point to lower in step with temperature. So what would our dew point be at 1,000 meters in that case? What would our dew point be at 1,000 meters in that case? See a couple of votes for 0. And that is correct. So when a parcel of air becomes saturated, the temperature and the dew point both cool at 6 degrees. They both cool at a rate of 6 degrees. They both cool at a rate of 6 degrees. So when the parcel's unsaturated, the air temperature is cooling by 10, the dew point is cooling by 2. Once the parcel becomes saturated, the parcel cools by 6, the dew point cools by 6. So it's 10 and 2 for unsaturated, 6 and 6 for saturated. 10 and 2 for unsaturated, 6 and 6 for saturated. Let's do an example. So we have an air parcel with a temperature at the surface. So here's our surface of 30 degrees. That's going to be our first column. And a dew point of 14. What's the very first thing I want to do before I start these parts?
Find out if it's saturated.
Bingo, Daniel. Check for saturation. In this case, is our parcel saturated or not? In this case, our parcel is warmer than our dew point. So in that case, it's saturated. What would our parcel's temperature be at 1,000 then? In that case. Remember, for an unsaturated parcel, you cool by 10. It's 10 and 2, 10 for the temperature, 2 for the dew point. So at 1,000 meters, temperature cools by 10. For our dew point, it cools by 2. So we have a temperature of 12. Okay, before we can keep going, we need to check for saturation again. Is our parcel saturated at 1,000 meters? No. Still unsaturated. So as we keep going up, we're going to keep cooling by 10 again. So our parcel at 2,000 meters is going to be what? I'm loving it. Our dew point will keep cooling by 2. So what will our dew point be at 2,000 meters? It will also be 10. So what has happened at 2,000 meters? Our parcel has become saturated. Here, the parcel has become saturated. So now we switch from 10 and 2 to 6 and 6. So what's our parcel's temperature at 3,000 meters? Four. Remember, once the parcel becomes saturated, instead of subtracting by 10, you subtract by 6. No big deal. That's what this is for. And then what about our dew point? We also subtract by 6. And just in case you're wondering, as long as the parcel keeps rising, the temperature and the dew point will continue to cool at the same rate. Because as long as the parcel keeps rising, the two are going to stay saturated. So this height right here, this magical height, where we switched from 10 to 6, where the parcel went from unsaturated to saturated, this actually has a fancy name. This is what is called the lifted condensation level. The lifted condensation level. This is the height that a lifted parcel condenses. So it is the lifted condensation level. Let's get practical with this real quick. So it is at this height, it is at that height that clouds form. So if you ever look outside and you see clouds, puffy clouds up there, what that means is that some rising air has reached the lifted condensation level, or the LCL as we call it. And it's at that height that clouds form. Once it reaches that height, the parcel switches from dry adiabatic to moist adiabatic. And we call that height the lifted condensation level, or the LCL. So we call that height the lifted condensation level, or the LCL. Now what's really cool is that when you go outside, you don't have to calculate anything to find the LCL. If you go outside and you see a cloud, the bottom of that cloud, the base of that cloud, is the LCL. The base of a cloud is the lifted condensation level. So anytime you go outside and you see a big puffy cloud, the bottom of that cloud is the lifted condensation level. That is the height that air has switched from being unsaturated to saturated. That is where the magical switch happens. So going back to our previous problem, the parcel's LCL was at 2,000 meters. And I will just keep going. So at 2,000 meters, the parcel had a temperature of, if I recall, sorry, this will take a moment. Okay, yeah, the parcel had a temperature. The parcel had a temperature of 10. No, that was 3,000 meters. I lied. The parcel had a temperature of 10, and the dew point was also 10. So this was actually a different problem. I'm sorry. Well, in that case, I will start over. At 0, the parcel was 40. The dew point was 16. At 1,000, the parcel was 30. Dew point was 14. 2,000, parcel was 20. Dew point was 12. Because that's an ugly 12 too. 3,000, the parcel was 10. Dew point was 10. At 4,000, the parcel is 4 and the dew point is 4. What about at 5,000? What would my parcel's temperature be? So the parcel was 10 degrees at 3,000 meters. The dew point was 10 degrees at 3,000 meters. We went up to 4,000 and they each cooled by 6. What would our temperature be at 5,000 meters? Our temperature would be -2, and our dew point would also be -2. In this example, everything below 3,000 was unsaturated. Everything above 3,000 was saturated. And that boundary is the LCL. All right, last thing I'll talk about. Let's apply this to our big precipitation difference between us and Santa Cruz. Because that's what everybody came here to hear about. Not really, but. Now what happens is, if a parcel sinks, another crazy phenomenon happens. Nice. As the parcel sinks, the exact opposite happens. Once a parcel sinks, it immediately begins to warm. Moisture that had been wrung out of the parcel as it was rising does not return to it. So what happens is, the moment the parcel begins to sink, it is unsaturated. The moment the parcel begins to sink, it is unsaturated. And so as it's sinking, it will warm dry adiabatically. And this is really important because this is what allows us to see the difference between San Jose and Santa Cruz. And here's why. So Santa Cruz and San Jose are only about 25 miles away. Whoops. They're only about 25 miles away, but they get very different precipitation amounts. Santa Cruz gets twice as much rainfall per year than we do. And the reason why is the Santa Cruz mountain range. That is the #1 reason why. Because as moist air hits the Santa Cruz mountain range, it is forced to rise. As it rises, a lot of the moisture that is in those parcels of air condenses and is wrung out. Then once it hits the peaks and then comes down the other side, it warms back up dry adiabatically, but that moisture doesn't return. So by the time the air reaches San Jose, it is warm and dry. So this is because of what is called the rain shadow effect. This is why we don't get as much rain here. What happens is, as air rises up a mountain, it cools and condenses into clouds. Those parcels of air lose that moisture. Remember, as soon as moisture condenses, it is no longer a part of the parcel. So that parcel, as it's rising, it's losing moisture, losing moisture, losing moisture, and it never gets it back. So as the parcel sinks down the other side, that moisture doesn't return. So the parcel begins to warm dry adiabatically. So by the time it makes it down to the other side of the mountain, it is hot and dry. It has lost its moisture. It has gained latent heat. Therefore, it is hot and dry. And we can actually see this when comparing Santa Cruz's climate to San Jose's climate. Yes, San Jose is a little bit more inland than Santa Cruz, but that's not the big reason. The big reason is because of the mountain ranges. If it was all flat between here and Santa Cruz, we would get almost the same amount of rain as they do. But because of those mountains, they get more and we get less. So this image just kind of demonstrates that. When air comes up over here on the Santa Cruz side, that's what's called the windward side of the mountain. It expands, cools, and condenses. Once it sinks down the other side, it compresses and it warms, but it's lost that moisture. Now, I could break this down a lot more, but all I really want you to know is that as air goes up and over the Santa Cruz Mountains, it loses moisture because it cools and condenses. And that's it for today. Just really quickly, the difference between Santa Cruz and San Jose. Not only are we drier, we are warmer. So all of that being said, really quickly, our next quiz has just opened up right now. So that has just opened up. You have until Sunday to do it. One thing that somebody asked me about last night, there was a problem that they had with viewing some of these lecture videos. What I found is using the player that's embedded in Canvas is not good. So if you actually go to the link right above that, the title like right above the player, click on that and it'll take you directly to the YouTube page where it will work. And that's it. If you have any other questions, comments, concerns, I can hang out. Otherwise, it should cool down this weekend. It's going to be hot today and tomorrow. Try to stay cool, everybody. Bye.
Thank you. Have a good weekend.
Take care.
Bye.
Bye.
Professor, I had a question.
Absolutely.
So I was about term actually in the future, because one of my family members had passed away, so I'm going to be out of town, and I wanted to know if it's going to be in class or online.
Are you talking about the upcoming midterm?
Yeah, and October 15th, I believe.
Yeah, it will be actually structured very similar to the way that these quizzes are. The only difference is you'll once you start it, you'll have a time limit, but you'll be able to take it anytime between that Thursday and that Sunday.
Okay, sounds good. Thank you so much.
Absolutely. Any other questions I can help out with? Anything else? Oh, sure. Let me, yeah, absolutely. Here, let me open up a breakout room. And I could put us in there. And then, all right, you're gonna get an invite to join a breakout room, and then I will be in there in just a second. I still see 2 people in here. Do either one of you need any help or need anything? If not, that's totally fine. I just want to make sure that I'm not abandoning you. Well, as always, please send me an email if you need any help. And I will see you next time. Bye.